Okay, so would you be happy that on this sheet we have seen 3 types of transformations? Okay, does anybody want to give me one of the types of transformations that we've seen? A reflection. Good, I'm going to put reflection down here. Okay, can somebody give me another type of transformation?
Explorer.
Okay, so what do we call that? What's the special name for that? So if somebody picks up the graph and pulls it one way or the other, it's a stretch. Good. Okay, what's the last one that we've seen? Yeah, what's the special word for moving it or shifting it?
Shifting it.
Begins with a T. Good, it sounds like transformation, but it's a translation. Good. But to be honest with you, if you say shift, that's totally fine. Okay, anybody would know what you mean if you meant shift. But try and use the correct language, like translation is better. Okay. Now, would you be happy that all of these transformations have happened either in the x direction or in the y direction? So moving left and right, x direction, moving up and down, that's the y direction. Or likewise, a reflection has happened in the x-axis, the x direction if you like, or the y direction, the y-axis. Okay? Or the stretch, somebody's grabbed it and pulled it upwards in the y direction, or kind of gone like that in the x direction. Okay? So, let's think about this. Let's suppose we take the graph y equals x squared. So I'm going to draw that in the top right-hand corner up here, okay? Because it's a graph, I think, which we're most familiar with. I don't particularly want to use linear graphs because I think x squared graphs are slightly more exciting. They slightly illustrate the picture better. But I can use any graph I like, okay? So, let's think first of all. Let's think. I'll just wait for Tiffany to come in. Would you be happy that I could say this graph is y equals x squared? Would you also be happy that if I used function notation, I could write f of x equals x squared? Now, who in here has seen that notation before? F of x? No one. Okay, so all I want you to think about, you remember my functions which I was drawing in the first half, okay? That's all f of x means. Okay, so f of x just tells me what I should do to my inputs. So if I say that my input is x, like that's the value that I stick in, what should I do to that value? I should square it. That's my function. It's simply just saying square it, all right? So this thing and this thing are entirely equivalent to each other. I'm just going to think of it in terms of f of x. Just remember x is my input. All right, okay. So let's suppose I want to visualize the graph y equals x minus a all squared. Okay. Would you be happy this is happening in the x direction? Yeah, so it's happening in the left and right direction. What's happening? Can somebody describe this transformation fully? If I tell you to draw the graph y equals x minus a, just like I did on this sheet here, okay? If I ask you to draw the graph y equals x minus something, whatever a is, all squared, what would I be thinking about? What's the transformation that's happening here? By a. Yeah, good, in the x direction, okay? So this is simply a translation in the positive direction by a, in the positive x direction by a. How could I write that as a vector? How could I write that as a vector? So a vector is a bit like a coordinate, but it's just been rotated through 90 degrees. Perfect. Yeah, we all happy with that? Think of it like a coordinate. So think of it like this. You're all happy that that means that's how many you move across, that's how many you move up and down. It's a similar kind of idea as that, except it's not a coordinate, it's not a point, it's a movement that's happened. So I write it as a vector, which is as a column, okay? So if you see that, think of it as a coordinate in the sense that that's how many you move left and right, and that's how many you move up and down, but it's written as a vector because it's not a coordinate, okay? Now, if I wanted to quickly sketch this graph, I would have something that looks like this, okay? So that point there would basically be a. It's moved a to the right. So if this was x minus 3, it would move 3 to the right. If this was x minus 10, it would move 10 to the right. If this was x minus 1,000, it would move 1,000 to the right. Does that make sense to everyone? Okay. Now, what if I didn't want to move it to the right? What if I wanted to move it to the left? How would I adapt this? Good. So it'd be x plus a all squared, okay? Which in this case would be negative a 0, okay? If I wanted to sketch that, I would have something like that. So that point there would be a. Good, okay? Does that make sense to everyone? Does that make sense? Okay. Now, do you notice this a bit weird? Because it's the opposite of what you think. And we've kind of looked at this briefly when we looked at quadratics, and we kind of highlighted this. So it's happening in the x direction. You see the minus a, and you think, oh, okay, that should be moving a to the left in the negative direction. But it's not. It's moving in the positive direction. And the same thing here. You're seeing the positive a, you're thinking it should be moving to the right in the positive direction. It's not. It's moving in the negative direction. So think about it. With the x direction, with the translations, it's the opposite of what you think it should be. So if you see the x minus a, whatever it might be, then you can think about this as it's moving in the opposite direction to what you think. Okay? If I wanted to do this more generally, so let's imagine it wasn't the squared graph. Let's imagine that this was just any function you like. What I could do is just replace it like that. Okay? So instead of writing y equals x minus a all squared, I'll just write f of x minus a. And the same thing down here. So for example, I'll just use it for space, but I'll rub it off in just a second. If my function was x cubed, okay? Well, I could use a similar kind of idea here. I could just say, okay, x minus a all cubed would basically move the cubic graph a to the right. Yeah? Or if I wanted to do x plus a all cubed, it would move the cubic graph, which remember looks like this, a to the left. Okay? So by just using functions, it's basically saying any function you like. If I use this kind of idea, if I replace the thing inside the function with whatever I need, x minus 3, x minus 2, then I can just think about the entire function as moving. All right? What would this thing be? Okay. Does anybody remember what the graph 1 over x looks like? Yeah, good. It's that. I call it the butterfly graph because I think it's kind of quite pretty. So that's the butterfly. Oops. That's the butterfly graph like that. Okay. Well, if I wanted to do f of x minus 2, okay, how would I write the equation first of all? How would I write the equation? So remember, it's the x which I'm changing. I'm changing the x to x minus 2. So it becomes 1 over x minus 2. That's all I'm doing, just replacing the x with x minus 2. Okay. So what's the transformation that's happened here? What's the transformation?
First of all, negative 2, so it's moved to the right by 2.
Exactly right. So I take this graph here, and I just shift it all to the right by 2. So if I think about that, okay, that's gone to the right, and that's gone to the right as well. I guess here I should draw my asymptotes in. So remember, my asymptotes go like that and that. So therefore here, my asymptotes are like that and like that. It's just been moved 2 to the right. Is that okay? Yeah? So just think, all I mean here with my function is it's just my x which I'm changing. So I'm changing my x to be x plus a, or x minus 2, or x plus 3. It doesn't matter. Okay? I'm just changing my x. So this is the reason why I got you in the first half to draw these different graphs. Because once you know how to draw the plain, vanilla, basic graphs, you can think about the transformations that have happened from that. Okay? And you can get any graph you like.